Thanks for inviting me here to give the talk. Can you hear me from back there? Okay. So what I'll talk about this talk is hopefully some new ideas for some of tools that I think that from what I know happens quite often in machine learning. The perspective that I come from is I'm a student who. So my main area is in theory, so I work on efficient algorithms. So I'll take the perspective of a theoretical analysis of these algorithms. And the question that I hope to get some answers from you about is whether these algorithms actually work. So is there some kind of practical use of these algorithms? So the talk will be structured as follows. I'll first describe the variance optimization that I'll talk about, and just give some motivations of why these are interesting problems to look at. Then I'll talk about what I consider to be the key optimization problem, which is quadratic minimization or L2 minimization. And then I'll use this as a subroutine to describe some extensions to solve optimization problems in L1 norm and other norms, so P norm in general. So one way I like to think about the one way I like to generalize a lot of these problems that seem to happen in machine learning. So after all, I'm a theoretician, so I like to generalize about things. So one way I like to think about things is that you're given an input signal that's potentially noisy, and you're trying to recover some kind of structure, you're trying to infer some pattern from it, you're trying to get some kind of you're trying to basically compress it into a small, you're trying to make sense of it, basically. So one way to think about it, you're trying to find hidden pattern in noisy data. And one tool that seems to be used a lot to address this kind of problem is the idea of setting up an optimization objective and then minimizing. So you set up an energy function representing some state of your problem, and hopefully by minimizing this energy function, you get something that's close to the answer. So the typical form of such a problem is I want to minimize the p norm of a vector, where p is some constant at least 1, so it's a convex objective, subject to some constraints. So these constraints are usually convex constraints. For simplicity, the simplest version of them are linear equalities. So you're trying to optimize some energy function in a subspace. So I claim that this kind of problem occurs almost everywhere. And let me just try to convince you with a few instances of it. So one of the most popular instances of convex minimization that you probably see in machine learning is probably the last objective, which is to minimize the one norm subject to linear constraints. So this actually has motivated an entire area known as compressed sensing. And the reason this is a useful objective is it tends to give you a structured and sparse output, and it's very robust to noise. So it has also some nice properties in terms of recovering a good answer. Also, the other setting which I've looked more at personally is the setting of image processing, where it seems a lot of these image processing objectives tends to become minimizing some type of energy function, for example, total variation or hinge loss functions. So here's an example of a framework known as Poisson image processing, where the idea is you have a gradient between the pixels. So you set up pixels as entries, and you have some kind of gradient on this image. And you want to find values such that the new gradient, your new discrete gradient, is as close to the actual gradient. So you're trying to minimize the L2 distance between your target gradient and a gradient you can get. And you can use this framework to do a lot of things. Actually, in the Poisson image processing paper, I think they show 5-6 applications. The one that I'm showing here is blending. So you can take two things that may or may not belong to each other. So this is a picture of a polar bear, and the background is a picture taken by a planetary rover. And it turns out you can just blend them together, and it doesn't. Well, I'm not sure how much you can see from this projector, but I think at least it looks kind of real. So the other instance, so you can also use optimization objectives to do a variety of other things. So this is an instance of separation. So this is support vector machines. It's an instance of semi-definite programming, where the idea is you have some points labeled 0, some points labeled 1, and you're trying to find the largest margin of separation. I think a lot of these classifiers based on separation can be written as optimization objectives as well. So due to the prevalence of optimization objectives, not just in machine learning, but also in operation research, and actually computer science combinatorial optimization in general, they're actually one of the most studied algorithmic topics. It's kind of interesting that the study of these algorithms potentially fall into 20-year intervals. In that, and actually, I think, well, so my impression is that some of the work on them actually predates the introduction of computers. They had huge rooms of people just trying to minimize one of these objectives. So what they were concerned when they started working on this is whether the problem is just tractable. So this led to simplest algorithm, KPD conditions, and by the mid-50s, they were reasonably comfortable with solving small size, so 10 to 20 variable optimizations. And then theoreticians went and tried to figure out whether this problem is polynomial time. And this led to the ellipsoid algorithm, which is polytime, but has a huge polynomial dependency. So this deficiency led to further studies, and it also led to new ideas such as interior point algorithms, log barrier methods. And by the 2000s, they were able to get, with a lot of effort, about an m to the 2.5 time algorithm. So here, m will denote the number of non-zeros in the problem. You can think about it as the problem size. So this is essentially the state-of-art theory results on this. But unfortunately, the issue that we deal with now is that it's very easy to get a problem size where m is at least 10 to the 6. So your cell phone camera has 10 to the 6 pixels. And if you go to, say, medical data or 3D images or videos, you can easily get to 10 to the 9 pixels. And my general impression is that a lot of data is at least 10 to the 7, 10 to the 8. So even if you do some trimming on the data, you're still very quickly at about 10 to the 6 size instances. So here, if you combine this with the bound of m to 2.5, that's a little cost prohibitive. So my impression is that what's actually done for minimizing these objectives are first order methods. So the idea is that you take some kind of coordinate or gradient descent. There's also a stochastic method that samples the data as you go. So you calculate the gradient with respect to only some subset of the data. And these methods are very widely used in practice for several reasons. First one is simple. You can code these methods in MATLAB. It's like 20, 30 lines of code. Also, it works. And you can also show that they converge very fast when the data is somewhat structured. So when your data has good structure to it. However, what I think is missing from these methods is that they have a lot of trouble dealing with ill-conditioned data. So for example, here in this example, my space is slightly skewed in one direction as opposed to the other one. So now the gradient descent takes this very long sequence of steps to get to the optimal. And this is actually just a case of quadratic, so you can actually have a very good feel of how the direction should look like. And the other issue is that coming from the perspective of a combinatorist, is that gradient, even though it's a very inexpensive operation for most algorithms, it's actually a rather expensive routine. To compute a small modification to your problem, you actually need to look at your entire space. So for example, if you're stuck kind of in this corner, usually you're only 2 or 3 constraints constrain your descent. So there's actually a very small part of the problem that's constraining your entire optimization. But for these gradient descent methods, because the way they compute the gradient, they actually have to look at the entire problem. So the question that I want to try to ask for the rest of this talk is that can we actually do better by first of all looking at the structure of the problem? So if we're stuck with only 2 or 3 constraints, we only look at these 2 or 3 constraints. Also, can we make more informed steps? So can we, in the case of say of a quadratic bowl, just figure out directly that we want to get to the minimum? And can we do this faster than, well, about as fast as finding the gradient? And to start off with, I'll talk about the setting of L2 minimization, which is quadratic minimization. This is actually one of the easier instances of convex minimization in that, as I will show in a bit, the problem, there's a very nice closed form for the answer. But then but this also gets used as a subroutine. So I will also show ways of extending methods using quadratic minimization to other types of minimization as well. So to recap, quadratic minimization is I want to minimize the 2 norm of some vector subject to linear constraints. So here I will have minimize the 2 norm of a vector y, so just Euclidean distance, subject to the constraint that y equals ax plus s. So y is just in some subspace. And so the notation I'm introducing here is that A is a matrix. It's an n-row d-column matrix.
How come that's an ellipse instead of a sphere?
Oh, so I think I'm drawing this in x instead of y. I think the right picture here, is, well, the other picture you can draw here is that I have some space. Do you see a chunk somewhere? So the other picture that you can draw here is that, well, the more correct picture is that I have a ball, and I have just some subspace, and I want to just find the closest distance to it. So this picture is actually drawn, yeah, this picture probably doesn't really correspond to this diagram, but hopefully conveys some intuition of what's going on.
If you substitute z equals ax, then that's the constraint for z. Yeah, it's an ellipse.
Yeah, I think I'm like plotting this in some other space instead.
Yeah, it could be X.
Yeah, so actually, I think what I'm actually plotting is I'm plotting this in X. So the way you can get this to a much nicer form to work with, so you can get rid of the constraint, because the constraint is just linear, is you can just substitute y equal to ax plus s directly into the problem. So now the problem just becomes minimize over all possible x of x transpose A transpose AX minus B transpose X, where B is a vector. So here you can think of A transpose A as a single matrix. So this A transpose A is actually what causes this distorted ellipse. So this kind of stretching of your space. And the way you minimize this is almost the same as how you would minimize a quadratic, which is that because it's a convex function, we know it's minimized when the gradient is 0. And you calculate the gradient in a closed form. The gradient is A transpose AX minus B. So the optimal happens when gradient is 0, which means that if you just set x to A transpose A inverse B, that's your answer. So quadratic minimization is essentially identical to solving linear systems, which, oh, okay, right. So it's identical to solving linear systems, and so it turns out that this kind of quadratic minimization, solving quadratics, and this closed form are all essentially the same problem. And solving linear systems happen to be one of essentially the oldest studied algorithmic problem. Well, maybe like Euclidean algorithm is the other one that comes to mind. But it's one of the oldest studied ones. As early as first century CE, there were works in a Chinese math text about this. Newton worked on it. So by some interpolation, this also happens to be the most rediscovered algorithm, in the sense that every 300 years somebody comes up with Gaussian elimination. So in the theory community, there was a lot of work on reducing this exponent of 3. So in modern terminology, Gaussian elimination is an order n-cubed algorithm. And somewhat surprisingly, it was shown that 3 is actually not tight. You can get a 2.8. Unfortunately, this is probably the only practical algorithm in this line of work. And people then started working on the 3rd and 4th decimal place in this exponent. So now we're at 2.3727, and this is actually due to a result by a CMU alumna, Virginia Williams. But unfortunately, if you look at these results, your total is still at least m squared. So if you think about this in the setting of m equals 10 to the 6, this is still a bit of a cost prohibitive algorithm, and we're still better off doing gradient z. So for the next while, I will try to discuss some ways that you could get better, L2 regression or quadratic minimization algorithms, and I will show better algorithms in 2 cases. Well, the case I'll talk more about is the case where A is tall and thin, so the number of rows in A is much more than the number of columns in A. And the other case that I will mention, I'll mention the result is when A has a graph-like structure, but unfortunately I won't be able to go into too much detail about that. So the tall and thin setting, this seems to be a setting that comes up quite often in machine learning, which is that you have a matrix where the number of rows far exceeds the number of columns. So one way you can think about it is that you have a lot of data points in a d-dimensional space, and the number of data points you have far exceeds your dimension size. And the typical range of values is that n is about 10 to the 7, d is about, say, 1,000. So the other place where this kind of setting happens is also my impression that this also you might have seen this in the context of a kernel. So the kernel setting is that each column of A is a point, and you just want a pairwise dot product between the values of these points. So if you set each column of A to be an unvariate observation, then A transpose A is just a pairwise dot product between all your points. So, but when we view it in the setting of the problem, which is I want to compute A transpose A inverse B, this almost feels like an easy problem, for the reason that A transpose A is actually a very small matrix. So D is only about 1,000. So A transpose A is only about 1,000 by 1,000. And I think on MATLAB, inverting that kind of a matrix of that size is about 2 seconds. So aren't we almost done in some sense? Actually, the problem, not that somewhat counterintuitively here, does not come from computing A transpose A inverse, but in fact actually comes from computing A transpose A. So A has n rows, D columns. So if you use naive matrix multiplication, this computation takes about n times D squared time. So that's actually more by a factor of D than the size of A. So essentially paying an extra factor of about 1,000, with cache effect is about an extra factor of about 100, then looking at this matrix A. So one of the ways to speed up this kind of setting is this alternate goal of finding a smaller matrix B. So I want to find a matrix B with much fewer rows, such that B transpose B is similar to A transpose A. So suppose I can switch A from say 10 to the 7 columns to about 10 to the 7 rows to about 10 to the 5 rows. Then computing B transpose B instead of A transpose A is a much less expensive operation. And once you have A transpose A, you can do whatever with it. So the simple approach for generating this B, of course, is, well, the first thing that comes to mind is I'm just going to pick some rows of A randomly. I think my impression is that this, for a lot of well-structured data, this works really well. So for when the rows of A are essentially, a lot of them are redundant, this works well. But you can also think about pathological cases where this doesn't work very well. And the most pathological case you can think of is that I only have one non-zero row in A. Everything is 0 except one row. And here, you're only going to pick this row with fairly small probability. So if you pick 10 to the 5 rows out of a 10 to the 7 row matrix, you pick that row with a probability of, say, like 0.01. And overall, you don't get a very good convergence. So one way that in practice that people seem to get around this issue is to pick the rows with probability proportional to their row norm. So you pick the rows with probabilities equal to the length of the sum of squares of their elements. So because this is uneven sampling, so now we're doing non-uniform sampling of the rows. There needs to be actually some rescaling that happens that happens to keep the expectation the same. For this talk, I'll try to sweep that under the rug. So we're just assuming we're just picking some rows. It turns out in this case that there still exist pathological cases. And the pathological case is that when say for one of these columns, there's only one non-zero entry. And this entry turns out to have a very small value. So it doesn't even have a very big value. So here the problem is that the columns do behave somewhat independently of each other. So so in the case where the columns essentially don't interact, picking the row norm gives some noise in some space that I don't want. And my impression from what I've heard, so I used to think that this actually does better in practice than at least random sampling. But from what I've been hearing lately, this actually doesn't. This actually is pretty much comparable to random sampling. Maybe you're off by you're better by a factor of like 2 or 3, but you still have a lot of issues of missing some parts of your matrix when you try to do this kind of sampling. So due to the deficiency of this kind of sampling, there actually has been a lot of work in the intersection of theory and machine learning on getting better algorithms for doing this kind of sampling, for getting this smaller matrix B. So this was initiated by work by Mellon, who showed that you can do better than direct computing A transpose A. 2 years ago, there was work by Dremes et al., who showed that you can do this in about time that's nd log n plus d cubed, where this d cubed comes from inverting the matrix A. Well, inverting the matrix A transpose A. Last year, there was work by Clark and Woodruff, who showed a runtime of roughly number of non-zeros of A, so the size of A, plus d to the 4th. So slightly more than the cost of computing, than the cost of computing this inverse, but still, this is a much faster algorithm when the size of A greatly exceeds the size of D, well, the number of columns. And for the next while, I'll talk about a joint work with my advisor Gary Miller on an alternate approach for getting these sampling. So as it turns out, the hard part wasn't to get the optimal sampling probability. Well, the hard part wasn't to figure out what the optimal sampling probabilities are. There was actually a lot of work in statistics that figure out what exactly the right sampling probabilities will be. So they were worked by Holman and Welsh and Chattarjee, who coined the term statistical leverage scores. So I will not be able to describe what these leverage scores are, but you can think of them as these right probabilities that you assign to every row of A, such that if you sample by them, you get a good approximation, matrix B. And furthermore, what's interesting about these numbers is that the total probability, summing over all the rows of A. So if you add up these probabilities, the total is D. The implication of this is that if you sample by these probabilities, there exists a matrix B with about D log D rows, such that B is almost the same as A in the outer product sense. And the problem that exists in all of these works is how to find these leverage scores. The issue, though, is that you need the A transpose A, or some approximate of it, to get a good estimate of these leverage scores. And the problem there is you need the approximation B transpose B, and you're back to the same problem. So essentially, it's a chicken and egg problem, and essentially, a lot of the work in this area can be viewed as getting around this chicken and egg problem. So the way that we do this is that we partition A into blocks. And then we compress each of these blocks using just a random projection, so some fairly arbitrary compression method. And you can think of these blocks as fairly small, so about, say, each with 10 rows. So now we reduce the size of A by a factor of 10. We now go compute an approximate of it, as well as getting the leverage scores out of it. And then we use these leverage scores back in the original matrix A to do the sampling. So we can use this short version of a matrix to get a good estimate of the leverage scores in the big matrix. And this breaks the chicken egg problem because every time you go around this loop, every time you go around this loop, your problem size decreases by a constant factor. So by the typical analysis, you get a linear time algorithm as a result of this. So the result is that we can essentially find B with about order D log D rows, such that B transpose B is roughly the same as A transpose A, in roughly the time of number of non-zeros plus D cubed. So in a setting where number of non-zeros is about 10 to the, say, 10 to the 9, and A has about 10 to the 3 columns, these two terms are roughly the same. And you get a linear time, essentially you get a linear time algorithm for reducing the data size that I showed you earlier to a much smaller data set. So the other thing that I'm kind of interested in about this kind of sampling mechanism is there any kind of semantic interpretation of the set of rows that you can pick out? So the understanding that we have about this is mostly in terms of condition numbers, so in terms of these matrix approximation factors. So one thing that we're trying to think about is whether there's any kind of good interpretation of this kind of sample that you pull out. And this kind of idea actually has been extended to another setting where there's a lot more structure in the matrix, which is a setting where A has graph-like structure. By graph-like structure, I mean that A is related to the edge-vertex incidence matrix of some graph. So here the idea is that each row of A corresponds to an edge in some graph. So you have a 1 and a -1 in 2 columns, corresponding to an edge between those two vertices indicated by the columns. And the goal here is trying to approximate a solution to A transpose AX equal to B. And the difficulty with graphs, so although graphs have a lot of structure, there's also a difficulty in doing this for general graphs. So you're probably aware of these fairly unstructured graphs, for example, a social network graph. There are also adversarial graphs, such as expanders. Yes. Sorry. So the issue in general with these kind of settings is that it's very easy to find instances where the problem is unstructured, and it's very hard to decompose your problem. So actually, for a lot of these gradient descent type algorithms, a case where that's actually very problematic for them is also the same case that's very problematic for purely iterative methods for solving graph-based linear systems, which is my graph is just long and skinny, so it's just almost like a line-like structure or a grid. So there was quite a bit of work on this starting in the early 90s, and this culminated in a result by Spielman and Tin, who showed that you can essentially solve systems related to graphs, linear systems related to graphs, in time that's nearly linear in the size of the problem. So the theoretical definition of linear running time is actually m poly log n times log 1 over epsilon. So notice that there is an epsilon error here, but the dependency on epsilon is fairly mild. But the bigger issue with this theoretical definition of nearly linear is that in theory, we think of any factor of log n to the power of c as essentially a constant. So I've actually never really figured out what exactly this value of C is. So I'll just resort to authority and show you some estimates. What the estimate I've heard from Dan Spielman is 70, so log n to the power 70. My advisor Gary Miller claims 32. Co-author Yannis Koutis claims 15. Shanghua Chen claims 12, and the lowest I've heard is 6. Well, before our work. So the issue is that when m is about 10 to the 6, log n to the power of 6 is essentially 10 to the 6 as well. So this is almost no better than an m squared algorithm. And in a joint work with Yannis Koutis and Gary Miller, what we showed is that you can get this C down to 2. So it's still a pretty big factor, but at least it's a much simpler approach. And the general idea there is once I get to drop rows. So the idea is I have a graph. I want to modify it in some way to get a similar B. And you can compute probabilities of each row using a much more intricate scheme based on finding a good spanning tree of your graph. And then with these right probabilities, you can sample the graph down to a smaller graph, so this kind of graph on the right, which you in turn shrink with a variety of other methods, and you repeat. And we also, so subsequently we also showed that this method, if you look at this method in a more streamlined fashion, you can actually get down to a running time that's roughly m log n. So, but this is still not really linear in the sense that log n is still a factor 20. So in practice, there's a solver package developed by Yannis Koutis and Gary Miller, two of my co-authors. It's called the combinatorial multigrid solver. It actually uses a whole bunch of ideas from scientific computing, numerical analysis, and the whole area of multigrid solvers. So it uses a lot of the tools in conjunction with these graph theoretic-based ideas. And the last time I checked, so every time I check about the running time, I get a different number that's smaller than the last time I checked. Kind of like the exponent on log n, except this is actually the constant factor. So last time I checked, I heard that the time it costs to do one of these solves on a sparse graph. So on one of these sparse, fairly has some kind of planar-like structure graph, you could get a time that's roughly 20 matrix vector multiplies. So it's almost comparable to a forward matrix vector multiply, as we call it. So this is an example of using this algorithm for segmentation of the scan of a retina. So this is a picture of a scan of somebody's retina, and you're trying to separate out the layers of the retina. And the colored lines are just cuts generated by this algorithm. And you can download this package at cmu.edu jkoutis cmg.html, and I'll show this link again at the end as well. So this is all I want to say about quadratic or L2 minimization. But from the start, I was hoping to talk about general convex optimization. So I did kind of a bait and switch on it. So now I'll go back and talk about L1 minimization and general minimization in general norms. So the problem that I started off talking about is I want to minimize the p norm of a vector, subject to some constraints. What I've done is I cross out this p and put in 2. So once again, I'll resort to the theory, well, magical results in theory. Let's say essentially that convex optimization can be reduced to square root m quadratic minimization problems, which is by setting up the correct barrier functions, you can solve about square root m L2 minimization problems to put together a solution to one of these convex optimization problems. So this is what theory says. In practice, I will quote Boyd Vandenberg. And what they say is that the growth in the average number of iterations, so the number of quadratic minimization problems you want to solve to piece together a good solution, actually doesn't grow much. So here's a plot. I think this is on the horizontal is the log of the problem size. Vertical is the number of iterations. As you can see, it doesn't really grow much. But if you're sharp-eyed, you'll also notice that this number here, they only go up to about 10 to the 3, so about 1,000. And this actually has to do with the fact that we can't really solve general linear systems very well. So in general, this approach has a lot of issues when dealing with general convex optimization instances.
10 to the 3 isn't the log of the problem size.
No, it's not the log, it's the problem size. So it's a log plot. So this is size 10, size 20, size 100, size 1,000.
Oh, okay.
So they took log when plotting the x-axis. I think in general you can get to, I think these days you can probably get to 10 to the 4, but probably not much more than that with this kind of method. But what we just showed is that for a lot of these quadratic minimization, you can actually do them extremely fast, especially for these graph-based variants. So if you look at these methods, turns out you can actually substitute. You can substitute general linear system solve with these fast quadratic minimization methods as an inner loop, and then see if you can get a better algorithm. And you do get a fast algorithm this way. But the issue is that if you look at the results for this reduction, so this going from H1 to going from quadratic to general minimization, it's a bit of an opaque black box. It's very hard to pin down what exactly is going on in this algorithm. So what I'll talk about for the rest of this talk is are there more natural and more lightweight methods for making this transition and solving optimization problems using quadratic minimization? And the problem that I'll focus on is this lasso problem. This was this kind of like the canonical non-quadratic minimization problem. So here I want to minimize the one norm of some vectors subject to some constraints, some linear constraints on it. So here there were some recent results in theory by Cristiano, Keller, Maudry, Spielman, and Ten, who showed that you can approximate the minimum cut problem on a graph using about m to the 1/3 iterations. So instead of m to the half, they get m to the 1/3 iterations as well. And the reason that min cut is an interesting problem from a theoretical point of view is that it's almost like the canonical L1 minimization problem. And so there's very natural hopes that you can extend this L1 minimization problems. Well, you can extend their algorithm to general L1 minimization algorithms. And here's the general idea of this algorithm. So I want to minimize the one norm of y, subject to that linear constraint. I will not put the constraint on the slide for just for simplicity. So I want to minimize the one norm, which is summing over all entries of the absolute value of that entry. So they take this quadratic relaxation. So the idea is essentially what's called iterative related least squares in statistics. And the idea is I want to pick weights, one for each entry, then minimize a quadratic variant of it, which is summing over all entries of entries squared divided by the weight. So this is a quadratic minimization problem, and you can apply all the fast quadratic minimization algorithms to it. And the reason these weights are useful is that they are essentially serve as guesses on the absolute value of the yi entries. So notice that if you happen to guess them exactly right, so if you happen to guess the case where wi equal to the absolute value of yi, you get that yi squared divided by wi is essentially just the absolute value. So if you do converge, you do get the right answer. And what they showed in their work is essentially that this converges very fast. So theoretically, you can show that about m to the 1/3 iterations suffice. And when we actually look at practical variants of this, you also don't see this m to the 1/3. So it's almost the same kind of situation with the interior point algorithms, except here you have a very good grasp on what every term of your algorithm means. And the reason, and going back to the formulation of L1 minimization, the reason we want to solve these problems is that they give a sparse answer. And the reason that you get a sparse answer is because the L1 ball, the L1 constraint on your space is a very jaggy object. So if you apply this constraint and you try to meet some subspace at it, chances are you'll hit it on a corner. So it tends to give you very good 0-1 solutions. But when we were looking at this, we noticed that there were actually a whole bunch of instances where we really don't want exactly sparse, like the sparse answer we want isn't exactly in the y space, so in this space. We actually want sparsity in some different space. And the simplest instance where we found this situation to show up, we encountered this situation, is the case where we were trying to process colored images. So now we have 3 values per entry. And we don't really want to get sparse primary colors. We just want entries to have sparse values. So you want some entries to have sparse, so you want a few small spots in your space, but you really don't want primary colors. So the idea is that you want to group some of the entries based on priors that you know about the setup of your space. And this led to the idea, well, this was also a known idea. This was the idea of group lasso. So the idea is you want to minimize summing over some groups of the 2 norm of some subset of your values, subject to the same kind of constraints. So here the groups are given as part of your input, describing how coupled some of your entries are. And it turns out that almost anything can be related. For example, going back to the image processing instance shown earlier, you can couple all the pixels in the bear, for example. And this essentially gives you a way to force known structure onto your data. And as it turns out, this is just a close cousin of the L1 minimization problem. In the sense that you can view L1 minimization as just absolute value of entry is entry squared to the half. So it's essentially the 2 norm of a vector consisting only that entry. And so, which means that you can essentially apply almost the same kind of approach as before. So I want to minimize summing over groups of the 2 norm of the group. Oh, yeah, 2 norm of the group, right. Okay. So what I do is I pick one weight per group, and I sum over the groups of the quadratic relaxation divided by the weights. Once again, the weights are guesses on the 2 norm of the values in the group. So if you're lucky, you get that the weights are essentially the same. So the square and the weights cancel, and now you're back to the exact answer. So in a joint work with Minhong Chin, Alexander Maudry, and Gary Miller, we showed that it's possible to approximate this kind of group lasso objective. We actually term this the group least squares objective to solving about m to the 1/3 L2 square regression. And this turns out to essentially encapsulate a lot of the objectives that we see from image processing. And there were some extra tricks that we had to do to get this algorithm to work, which is that previous analysis relied on 0-1 solution. And also our analysis, we had to go through KL divergence. Well, we had to develop a new potential function that's based on KL divergence between the guesses and the actual answers to get to show good convergence. And as I mentioned, we were able to capture a lot of image-based objectives using this kind of objective. And the reason image-based objectives were appealing to us was that images are essentially graphs in the sense that you can view pixels as vertices, and you can view edges as just neighboring relations of pixels as just edges. And you can also encapsulate non-local methods, which add edges across your entire graph very naturally using this kind of approach. So the other reason is that we can do the quadratic regression on images in essentially nearly linear time. So here are some examples of applying our algorithm to known image processing routines. This is an example of the canonical total variation objective. We're trying to denoise images. And here is the effect of various objectives. L1 actually gives you sparse outputs, while just quadratic tends to blur the image for you. This instance here is actually kind of useful as a blurring routine of your image. And this is the instance of Poisson image blending, which you're trying to put unrelated objects onto each other. So you can take 3 unrelated objectives. Well, you can take 3 unrelated objects and put them on top of each other and blend the texture. Also, this is the bear example shown earlier. You also do segmentation. So here's the retina scans. This is the noisy version. This is the version where you actually segment out the pieces. You're trying to get the layers. You're trying to figure out the nerve fiber layers. You can enhance text. And you also do global feature extraction, which is kind of related to blurring in that you want to remove the small objects from an image. And there are also some theoretical extensions that we worked out for this, which is K-commodity flow. We showed that it's possible to, in a joint work, this is joint work with John Connor and Gary Miller. We showed that it's possible to extend this kind of L1 minimization to essentially a dual problem of k-variant labeling of graphs. So this is instead of having 1 label per vertex, we have k labels per vertex, and then we have fairly intricate objectives between the vertices. So the edges consist of some more intricate function based on the difference of these k labels. So in summary, what we showed is that it's possible to for, in a lot of instances, to get faster optimization algorithms. And the way we do this is based on getting a faster routines for L2 minimization, and then using that as essentially the core routine for addressing a lot of these other objectives as well. So you can relax a lot of objectives with quadratic, and then use very intricate structures of these quadratic minimization problems to figure out better algorithms. And some of the things that we're trying to work on right now are, first of all, practical evaluation. So I think there's still some ongoing work about doing image processing with this kind of approach I just showed. Also, can we use this kind of approach to deal with other objectives? So the ones that we especially like to deal with are non-convex objectives. For example, hinge loss, where the idea is that instead of L1, once you're above a certain threshold, you just get the same value. So it's non-convex, but maybe you can still relax. You can still use this kind of relaxation approach to it. Also, as I mentioned, whether we can get an interpretation of the rows we sample from a matrix. So we have a very good idea what the probabilities mean now, but can we get some good interpretation of what sampling means that's outside of the spectral setting? Also, can we extend this kind of row sampling approach to LP norms and also low rank approximation of matrices? So in the case where your matrix is not just skinny, but your matrix is actually just a square matrix, but you know that there's a very good low rank approximation of it. So can you extend that to that setting as well? That's all.